In this section, we'll look at the components of the EdgeConnect SD-WAN ecosystem, specifically the trio of devices that make it all work. EdgeConnect provides advanced SD-WAN functionality for HPE's Secure Access Service Edge, or SASE. It is the WAN Edge portion of SASE, whereas the cloud security portion is covered with our Access SSE product. See the SSE Essentials course for more about these features. Ultimately, the goal of SASE is to deliver the best end-user quality of experience for cloud-hosted applications without compromising security. After working with many enterprises that have designed and deployed their SASE architectures, we've learned that basic SD-WAN functionality falls short. A business-driven SD-WAN like EdgeConnect with advanced networking capabilities is required to fully enable SASE, identify application traffic on the first packet, and granularly steer it to enforce both quality of service and security policies as defined by business intent. Keep cloud application definitions and TCP/IP address ranges up to date, automatically, every day. Automate orchestration between the SD-WAN and cloud-delivered security services from a single console to make it easy. Automatically fail over to a secondary cloud security enforcement point to avoid any application interruption. Automatically reconfigure secure connections if a newer, closer location to the branch location becomes available. And enable customers to adopt cloud security services and their SASE implementations at their own pace. And most importantly, provide the freedom of choice to deploy new security innovations as they become available from any vendor to easily address unknown future threats. In case you didn't know, software-defined WAN is not standardized. The term SD-WAN, or Software-Defined Wide Area Network, is something you might hear about from multiple sources, and each one says something different. At this time, there is no SD-WAN RFC or other specification for describing a universal standard on how it should work. This is because SD-WAN is an emerging technology, and each vendor in this area has their own proprietary solution. These solutions do not generally interoperate. Of course, here you'll learn about the EdgeConnect SD-WAN implementation, and how to use our devices to automate many aspects of your SD-WAN deployment and operation. Here we will discuss the trio of components that make up the EdgeConnect SD-WAN. The first is the Cloud Portal. Whenever you hear Cloud Portal, I would like you to think licensing server. It is the HPE hosted service that provides EdgeConnect SD-WAN and Boost licensing. Think entitlement of licensing via account name, account keys, and it even contains a database of device serial numbers for automated provisioning. Interaction is automatic. Other than making sure the other two components have internet connectivity to it, no customer action is required. It is completely managed by HPE. It does also house software upgrade image files and thus serves as a resource for the next two components for upgrading. The second component is the orchestrator. There is only one orchestrator per SD-WAN, which can manage thousands of SD-WAN devices. It must be registered with the Cloud Portal, and connection is via SSL. The orchestrator is what manages EdgeConnect appliances. Admins of an EdgeConnect SD-WAN log into their orchestrator, and all configuration of devices is handled within that single pane of glass. It is a very intuitive and user-friendly GUI that constantly communicates with every SD-WAN device to provide configuration, orchestrate tunnels, and provide monitoring information to the SD-WAN admin. The SD-WAN device itself is the third component, an EdgeConnect appliance. It is what receives configuration settings from orchestrator. It too must have SSL connectivity to the Cloud Portal and re-registers with it on a daily basis. This is the device that is responsible for handling all traffic, tunneling all traffic, or making decisions to send traffic not in a tunnel directly to the internet. In addition to Cloud Portal connectivity, the EdgeConnect must be approved and configured by the orchestrator admin. A good way to think about the orchestrator-EdgeConnect relationship is like a manager and its employees. The manager knows the big picture, has the team's goals in mind, and the employees each are instructed to go about day-to-day tasks doing the actual work. At its core, the EdgeConnect will act as a router. It will forward a packet between local interfaces if it knows which interface to use to reach the destination subnet. It could have this information as a result of being locally connected to the subnet, learning the route via routing protocol, or from a static route to the subnet. The EdgeConnect forwards traffic to the next hop router. How do EdgeConnect appliances learn about the different prefixes and subnets in your network? Subnet sharing is used between appliances to exchange information about locally attached subnets via IPsec tunnels. Appliances also support the BGP and OSPF routing protocols and can peer with third-party routers and Layer 3 switches, enabling them to learn additional routes and advertise routes known to the EdgeConnect appliances. Remember that the emergence of SD-WAN is a result of many applications and services moving to the cloud, such as Office 365, Salesforce, increased use of social media for businesses with Facebook, LinkedIn, Instagram, as well as infrastructure as a service solutions like AWS, Azure, and Google Cloud. This type of traffic makes sense to directly forward out to the internet instead of traditionally forwarding it to a data center. In this case, Laptop L is accessing YouTube, Office 365, or Facebook. Likewise, trusted apps such as these are also secured using their own encryption protocols, such as SSL, so there is inherent trust for such well-known applications. Typically, we know that this is internet traffic because the destination is usually to some public IP address. We call this internet breakout traffic. The other type of traffic that needs to be managed is internal traffic. Think of this traffic as anything you might traditionally have your laptop client access using a VPN, for example. We know this is internal traffic because it is destined for some private IP address. Server S at headquarters is on our internal company network. With software-defined WAN, the networking admin has more control and can efficiently manage internal traffic dynamically, especially with a business-driven SD-WAN like ours utilizing the orchestrator, which we'll look at in a bit. As you can see with the green pipes, we can utilize one or more different transport mechanisms and control how, when, and what traffic is handled. Here I'd like to discuss the various viewpoints one can have with respect to the EdgeConnect appliance illustrated. Unlike a traditional switch or router, an EdgeConnect has a very defined set of interface sides, LAN and WAN. LAN is self-explanatory, it's all the devices on your local area network. WAN is everything else on the other side. Note that it also includes other sites in your SD-WAN which exist out on the internet. There is also a distinct directionality to EdgeConnect traffic, inbound and outbound. When we want to analyze a flow, we need to first look at which direction it is happening in. Inbound is always traffic coming from the outside world, WAN, to the inside network, LAN. Outbound is always traffic originating on the LAN going out to the WAN. Many times, flows will be referred to in graphs, charts, and tables as inbound and outbound traffic. The key thing to remember is when we talk about traffic direction, inbound and outbound are referred to with respect to the appliance's LAN and WAN sides, or from the perspective of where the whole appliance is and not an individual interface, as is the case with firewalls, for example. This is where people confuse themselves. One of the default functions of an EdgeConnect device is to automatically build what are known as underlay tunnels between all WAN interfaces of each appliance. In addition to the physical name and number such as LAN 0, LAN 1, WAN 0, and so forth, Every interface can be assigned a label. This label can be something that identifies what it is connected to. Many times a descriptor for the transport type like INET1, MPLS1, or LTE1 is used. It can be anything the network design or architect dictates. Here we have 4 appliances that have interfaces labeled as INET1. In this case, all appliances will attempt to automatically establish IPsec tunnels to all other edge connects and terminate the underlay tunnels on their INET1 labeled interfaces. Likewise, all interfaces labeled as MPLS1 will also have underlays established between them throughout the SD-WAN. If an interface were to go down, then the underlay tunnel is torn down. Don't forget to permit traffic for the domains, addresses, and ports used by the appliances to create connections. Misconfigured firewalls are a common cause of connectivity issues. If you want a complete list of all the ports and protocols used by EdgeConnect, refer to the Orchestrator and EdgeConnect TCP/IP ports document at the website listed here. Let's look at encapsulation and tunnels between EdgeConnect appliances. We'll define both of these and see how it is done at a very high level. The basic job of the EdgeConnect is to form tunnels between each other as mentioned previously. Tunnels are logical connections between 2 devices, as shown by the orange lines. Tunnels are used to encapsulate data. Encapsulation is putting a data packet inside another data packet for transporting across the network. You should have some familiarity with internet addresses like websites, Amazon.com, YouTube.com, or how to get to internal sites like file servers, SharePoint, a coworker's laptop, and so forth using a distinct IP address. When you decide to browse to an internal server, your laptop composes an IP packet with the source address of itself, and the destination being the IP address of that server. That packet is sent to the gateway, where it needs to be routed. To keep things simple, let's say that EdgeConnect A is the default gateway for the internet at your remote office. So EdgeConnect A gets it and knows the file server is an internal resource. So it secures it by encapsulating the original user's packet with additional encapsulation information, namely its own address as the source and EdgeConnect C's address as the destination, as depicted in red. It then forwards the encapsulated packet over a tunnel to the remote EdgeConnect, in this case C on the right. When EdgeConnect C receives the packet, it looks at the destination address and says, oh, this is for me. So that's how it knows that it needs to do something with it. In this case, remove the red encapsulation header and forward the original user's green packet to the internal server. Note that the original user's data from the host was not altered. It was just securely transported across the SD-WAN tunnel in basically its own TCP/IP packet. In the previous slide, we saw encapsulation happen between 2 EdgeConnect devices, one adding the IPsec encapsulation header, and the other stripping away the same header at the destination side. Sometimes flows are not passed between 2 EdgeConnect appliances, and this is known as pass-through traffic. Any flow that isn't encapsulated, not in an SD-WAN tunnel to another EdgeConnect, is called a pass-through flow. This is because in today's cloud-first world where SaaS and infrastructure as a service are extensions of the enterprise network, it's critical for businesses to reach these cloud services by the most efficient and highest performing means. Frequently, cloud applications like Microsoft Office 365 perform better from home than from the branch, because there are local POPs much closer, spread throughout the world. This is called local internet breakout, and it's a form of pass-through traffic. In this example, traffic that is sent from a laptop in a branch office is broken out directly to the internet. Essentially, the EdgeConnect behaves as a router and not as an SD-WAN device. As such, traffic isn't optimized for pass-through flows. I want to clarify that pass-through traffic can be encapsulated inherently by the source application. Presumably, Office 365, Box, and Facebook traffic is protected using SSL encryption, for example. Technically, in an SSL or TLS tunnel. However, most of the time in the EdgeConnect world, when we use the term tunnel, people usually are referring to SD-WAN tunnels, specifically those established between a pair of EdgeConnect appliances. Pass-through flows, in turn, are usually reference to traffic not in an SD-WAN tunnel, or traffic that is being broken out locally. And that is essentially the trio of devices that make an EdgeConnect SD-WAN up, including some terminology like SD-WAN tunnel and pass-through flows. Let's go ahead and look at some review questions to check for your understanding. In the next module, we'll look at more details on the EdgeConnect orchestrator.